Hello. Today we're going to talk about how to generalize the idea of polar coordinates up until 3 dimensions. So the time when we're using polar coordinates is when we're dealing with regions that are best represented using radial slices. Um, so when we're talking about a generalization, we should expect that we are going to be talking radially in 3 dimensions. There are two different ways in which we can generalize these ideas of polar coordinates. First to cylindrical coordinates, and then to spherical coordinates. So let's talk about each of these two things. All right, so in cylindrical coordinates, instead of dealing with x, y, and z, we deal with r, theta, and z. So this is basically taking polar coordinates in the xy plane and then z coordinates in the z plane. So a point in space has some theta from the positive x-axis. It has some radial distance from the positive z-axis, and it has some height z in the z direction. So we can just think of this as taking a two-dimensional polar coordinates for your point, and then tacking on whatever the z value is above that. So when do we use cylindrical coordinates? What is the right frame for that? That's when we have a problem that involves symmetry around an axis. So you set your axis to be the z direction, and so that's if, let's say we have some cylinders that has symmetry about an axis. A paraboloid has symmetry around an axis, and as does some sort of cone, but we're going to talk about a cone that has a flat top, a flat base. So a cone that looks like this, like that. These are examples of things that you'll want to use cylindrical coordinates on. On the other hand, we can also use spherical coordinates. And this might have been what you imagined when you thought about taking polar coordinates to the third dimension. So what we're doing now, so instead of x, y, and z, we have three coordinates. Excuse me. This is a rho, this is theta, and this is phi. And these three numbers will tell us, also specify a point in our three-dimensional space. So if we have our point up here, it's some distance from the origin, and that's going to be our distance rho, the distance from the origin. Theta is the same idea, where it corresponds to how far from the positive x-axis you've rotated. But now we have one more piece of information that we have along with this, and that has to do with how far this this line has rotated down from the positive z-axis. So we have a line that's rotating the point. If you go from the origin to the point, that vector has been rotated down from the positive z-axis. And that is going to give us what phi is. Right? So what we're doing with spherical coordinates is we're talking about symmetry around a point. So if you have something where you have complete symmetry around a point, kind of like a sphere, so that's symmetric around the point. Or if you have some sort of spherical type of region, so a sphere where you take out the inner part of a sphere, that's also a region. A cone that has a curved base, so instead of before when we were talking about cylindrical coordinates, now we're talking more like an ice cream cone, where we have, it's a part of a sphere that's cut out by a cone-like direction. All right, so let's get into the nitty-gritty about how do you actually do that type of transformation. First with the cylindrical coordinates. So just this should feel comfortable. That is, if we have r and theta on the xy plane, and this becomes r and theta, then we already have the conversions between Cartesian coordinates in 2 dimensions and polar coordinates, right? These equations are exactly the same equations that we had in polar coordinates, and now we just have to say, well, whatever the z value is, that's your z value. So this is a nice extension. This is not adding too much complication. And similarly, when we're talking about cylindrical coordinates, just like we needed in polar coordinates to say dA is r dr d theta, we needed to be able to write down what a little bit of area corresponded to in terms of a little bit of r and a little bit of theta. Now we're talking about in 3 dimensions, so we need to replace our dv equals dx, dy, dz by a dv that's equal to some relationship with how little bit of radius we deal with, a little bit of theta that we deal with, and a little bit of z that we deal with. So if we're drawing a picture here, we've come out by a certain distance r, and so from this direction we get a little dr coming out in that direction. Theta, remember, a little bit of d theta is a little bit of an angle, and so that's going to give us d theta is an angle amount, so the width of this space here is r d theta. And then we get a little bit of z here to make a cube-like region, and that's r dz. And so what that's doing is that's telling us that one little bit of volume, when you have an r and a theta and a z, a little bit of each of those, the little bit of volume is going to be a dr times an r d theta times a dz, and so you get this expression that dv is r dr d theta dz. All right, so that one feels rather comfortable because we've been dealing with polar coordinates. Now let's talk about spherical coordinates. This is really where we kick it up a notch, and there'll be a little bit more memorizing, a little bit more working to understand what's happening. All right, so now let's go back and let's draw our picture about our point. So we've said that our point has some where we project our point down into the plane, and then this is theta. So if we look at this is our phi, and then the length of this line segment is rho. The length of this is rho. So what we need to do is we need to figure out what is the x component of this, what's the y component of this, and what's the z component of this, so that we can write down the expression for x, y, and z as a function of rho, phi, and theta. So let's work on this. So first thing we want to do is let's find what the z component of our point is. So let me use a different color here. So the z component, if we now draw this in the axis, if we look at what this looks like, where this is rho and this is phi, well, this z value is the adjacent part of this right triangle. So in terms of this triangle, what we see is this is rho times cosine of phi. So this is telling us that the z value that we get is rho cosine of phi. And so that's why if we have rho and phi, we can figure out what z is. Now I'm going to draw one more triangle here. And so this here is not in the x or y direction. It's something in the xy plane. So let's now take a look at what this value is. This value is going to be rho cosine of theta, sorry, cosine of phi. So that means that this distance here in the xy plane, which we're used to thinking of as r, right, r being the distance from the z-axis, r is going to be equal to rho cosine of phi. Okay, that's r. And so if we need to figure out what x is and what y is, we need to draw two more triangles. Right? We need to draw a triangle that says, all right, if this is theta, let me draw one more picture here. In my picture now I have the xy plane. And what we see here is that this was a distance r, sorry, rho cosine of phi. And so what that means that the x direction, if this is theta, is going to be rho cosine of phi cosine of theta, whereas in the y direction, that's going to be rho cosine of phi times sine of theta. Right, so that's where we're getting these equations for. So if we have rho, phi, rho, theta, and phi, then we can calculate x, y, and z. Let's say one more thing about this. We know that because this point here, this slice here, is from the origin to the point, we know the distance between those. That's x squared plus y squared plus z squared, and that's going to be equal to rho squared. So another clue to use spherical coordinates is you see a lot of things that look like x squared plus y squared plus z squared. So that's what we're going to use. I want to say one last thing, which is that what is the dv aspect here? So this one is probably something you're going to work to memorize. It's not beautiful, but it's saying, let's say there's a little bit of rho, a little bit of theta, and a little bit of phi. How do we calculate this little bit of volume that corresponds to it? I actually think I don't want to recreate the drawing, so if you want to look at the picture, it's on page 744 of the text. It has a really nice view of what this little slice is. So there's some amount of d rho that's coming outward. There's some amount of theta that you have down here. And so that's going to give a little slice here. And then you have some amount of phi, and so that's going to be a slice this way. So what you get is this little bit of the sphere. And then if you go through and you check all the different sides of this little box object, you can see that the contribution from this piece of volume is rho squared sine phi times d rho d theta d phi. And so that, whenever you do a triple integral using spherical coordinates, that you need that you have some contribution of little dv, then you need this whole expression to represent dv. All right, let's stop there. In the next video, I will do some examples of converting between the different coordinate systems. See you shortly.